In this video, we go over an example of a counter that counts to something other than a whole number power of 2. So this is a decade counter, which is the same thing as a 10 counter. And a 10 counter means that we'll count in binary from 0 to 9. Okay, remember 0 counts as a state, and the number 10 means that this counter has 10 distinct unique states at the outputs. Okay, so a decade counter, 10 counter counts from 0 to 9. Now here is the diagram of the decade counter, and notice that there's a NAND gate. And this NAND gate, the output is connected to active low clears of the JK flip-flops, and one input's connected to output Q3 and the other output is connected to Q1. All these JKs are in toggle mode, okay, just like the counter that we saw in the previous video. Now, I don't think I mentioned this in a previous video, but anytime you have a counter, whatever output is closest to the original clock input, that's your least significant bit of the count. So in this table that I have over here, see Q0, that's the least significant bit of our count. The output that's furthest away from the original clock input, that's the most significant bit. So Q3 here is the most significant bit of our count. And you see, it should make sense that the output that's closest to the original clock input is the least significant bit, because remember, each one of these JKs in the toggle mode will divide its clock frequency input by 2. So Q0 is half the original clock frequency, Q1 is a fourth of the original clock frequency, Q2 is an eighth of the original clock frequency, and Q3 is a 16th of the original clock frequency. So since Q0 is the highest frequency of all the Q outputs, it's going to be changing the most often. And that makes sense because in a binary count, the least significant bit is what changes the most often. Right? As you go from least significant bit to most significant bit, the bits change less often, as you'll see when we fill out this truth table, or this table here of the Q outputs. Alright, now notice that I have asterisks above Q1 and Q3. That's because those are the inputs to the NAND gate that are going to determine the output of the NAND gate. And I put the truth table of a NAND gate over here just as a reminder. So a NAND gate, the output will be a 0 only when both inputs are equal to 1. So you see, we have to keep an eye on the output of this NAND gate, because once the output of that NAND gate goes to a 0, it's going to activate these clears and make all the outputs of the flip-flops go to 0. See, because all the clears are connected together. If the output of the NAND gate is not equal to 0 and it's equal to a 1, well then the flip-flops will not clear and they'll just toggle, and we'll get the binary count that we saw in the previous video. So before we start to fill out this table here, it should make sense to you that if this NAND gate was not here, if we just had the 4 JK flip-flops, then this would be a 16 counter. But as you're going to see, by strategically putting this NAND gate where you see it, it's going to make this a 10 counter. Okay, because what's going to happen is that this NAND gate is going to make the counter clear when we get to a count of binary 10. Okay, and therefore we'll just count from 0 to 9. So let's see how that happens. And we're going to start with an initial count of 0. Now, we could start anywhere between, or we could start with any count from 0 to 9, and we would get the same truth table, or same table of Qs. Okay, I keep saying truth table. It's not really a truth table. It's just a table of our Q outputs. Okay, but I just decided to start at 0 since, you know, that's the minimum, and we're going to be working up to our maximum count of 9 here. Okay, well, with the binary count of 0, Q3 and Q1 are both 0, so the output of the NAND gate is going to be a 1. Okay, so that means that the clear is not activated, so when the next clock pulse comes along, it's going to increment our counter by 1. So we get a clock pulse, and the output of the counter is going to go from a binary 0 to a 1. Okay, Q3 and Q1 are still both 0. The output of the NAND gate is 1. So when the next clock pulse comes along, the counter outputs are going to increment to a binary 2. Okay, so you see so far this is no different than the 8 counter that we looked at a couple of videos ago. Okay, well now Q3 and Q1, well we got Q3 0, Q1 1, the output of the NAND gate is still a 1, so the counter continues to count, the next clock impulse comes along, and we're going to go to a binary 3. And you see the outputs of the counter are going to keep incrementing by 1 in binary as long as Q3 and Q1 are not equal to 1 at the same time. So we have a binary 0, binary 1, binary 2, binary 3. Okay, when we have a binary 4, okay, Q3 and Q1 are still not both equal to 1 at the same time, so the counter is going to continue to count. We'll get a binary 5. Okay, counter is going to still count because Q3 is still 0 here. So then we'll get a binary 6. Okay, continue to count. We got a binary 7. Okay, so you see this is the same as what we had for our 8 counter. Okay, Q3 is 0, Q1 is 1. So the clear is still not activated. So we get another clock pulse. The output of the counter will go to a binary 8. Okay, now Q3 became a 1 here, but now Q1 is a 0, so the output of the NAND gate is still a 1. So we'll still count. Got a binary 9. Okay, so output of the NAND gate still a 1. Next clock pulse, we get a binary 10, and voila, this is the first instance of Q3 and Q1 being a 1 at the same time. So now the output of the NAND gate is going to become a 0. And when the output of the NAND gate becomes a 0, it activates these clears and it makes the outputs go to all 0. And you see this binary 10 is only present at the output of the flip-flops for the amount of time it takes the output of this NAND gate to change from a 1 to 0. And the amount of time it takes for gate output to change is in the nanoseconds. You know, probably somewhere around 10 nanoseconds. This output will change and go from a 1 to a 0. So you see, we never see this binary 10. What we see is we see the output of the counter go from 9 back to 0. And then it would just continue to count again for additional clock pulses. So this count that the counter clears on, it's not present long enough for us to detect that it was ever there, so we never see it. So you see the way that we get this 10 counter is we strategically place this NAND gate, and when I say strategically, it's where we connect these inputs. Okay, because we connect these inputs at Q2 and Q1, that's what makes this clear on a binary 10. Okay, so for a 10 counter, we get the flip-flops to clear on a 10. If we wanted a 12 counter, okay, and a 12 counter would count from 0 to 11. So for a 12 counter, we would want the clear to happen on 12. So let's see how we can make that happen. Alright, so if we wanted a 12 counter, we would still leave Q3 connected to the input of the NAND gate, but instead of Q1, we would connect Q2. Okay, so we would remove, from the input of the NAND gate, we would remove Q1 and connect Q2. So it would be the same as just taking this wire here, breaking it, and then connecting it here. So you see now the counter is going to count starting at 0. It's going to count all the way to 9. And when we get to 10, see, it's still going to continue to count, because nowhere between 0 and 10 do we have a case where Q3 and Q2 are both 1 at the same time. So at binary 10, we get another additional clock input, and we'll get an 11. Okay, so still Q3 and Q2 are not 1 at the same time, so the output of the NAND gate is a 1. It's not clearing the flip-flop, so another additional clock input comes in. It will increment to a binary 12, and voila, this is the first instance where Q3 and Q2 are both 1 at the same time. So the output of the NAND gate goes to a 0. It gets cleared, so we would only see the output of the counter go from 0 to 11, then back to 0. We would never see that 12. Again, the reason you don't see the count that the counter clears on is because it's only present for about 10 nanoseconds or so, and our eyes would never detect it. So that's the key. To get whatever counter you want, you just need to put a gate such that it will clear the flip-flops on that count. So in the homework, I believe there's a homework problem where you're asked to do a 100 counter, so you'd have to figure out, well, what is the binary for 100, where the ones are in the outputs, and that's those outputs that are a 1 for a binary 100, those are the outputs you would connect to the input of the gate where you're going to use the output to clear the flip-flops. So, you know, if you have a 100 counter, it's going to take more flip-flops, okay, because clearly a counter with 4 flip-flops like this, the most it could ever count to is 15, right? 16 states, and that's if you didn't have a gate. So when you're doing these types of problems, first you got to figure out, well, how many flip-flops do I need? And that's just figuring out how many bits that you need for a maximum count. And then the other part of it is, okay, well, what inputs do I connect to my logic gate to get the clear to happen when I want it to happen? So you would want the clear to happen on a binary count of 100 for a 100 counter. If you're asked to do a 60 counter, you would want the clear to happen on a binary 60, and that way it would count from 0 to 59. So hopefully with what you learned in this video, you could come up with any type of counter that you're asked to do. And also if you were given some sort of diagram like the one here, you could figure out what counter we had.